Thank you for joining this lesson. We are going to study uniform circular motion. Just to define uniform circular motion, we can simply say that a uniform circular motion is the motion of a body in a circular path with a uniform speed. So if a body is tracing some circular path, then we usually say that this is circular motion. We usually say that the velocity of this body follows a given direction, such that if the body is cut off from the circular path at any given time or at any given instance, the motion of that body will follow the tangent of the circular path at that point. For example, the tangent to this point will be passing through the point like that, such that if the body breaks from the circular path, it will follow that direction with a velocity. If the body is moving at any other instance, like this one, the body, if it breaks from the circular path, will follow a path which is the tangent of the circle to the point where it breaks. Therefore, such a body is said to be in a circular motion. It is very important we mention that since at given instances, this velocity is changing because of the changed direction. Yes, the speed is the same or uniform, but because the velocity is facing different directions, then we say with change in time, there is a corresponding change in velocity. And due to that, then we say a body in a circular or a body in a circular path, a body in circular motion is said to be accelerating. It's said to be accelerating. Why? We say a body is accelerating when it is in a circular path because there is instantaneous. This is because there is instantaneous change. Instantaneous change in velocity with time. So as time varies or as time goes by, the velocity faces a different direction. And by that, because velocity as the aspect of direction, the velocity has changed. So we say that body is accelerating. It is important we define a few terms associated with uniform circular motion. Terms like angular displacement. Angular displacement. Angular displacement is abbreviated DITA. We usually say this is the angle swept by an arc at the center. So at the center of the circular path, the angle swept by any arc is called the angular displacement. Given a circular path like this, and now we are talking of a certain arc, maybe from point A up to point B on the circumference of the circle, then the angle which will be subtended at the center by this arc is called angular displacement. We call it angular displacement. This one is some displacement S along the arc length. So we usually say that angular displacement is given by the length of the arc out of the radius of the circle, out of the radius of the circular path. After that, we can define a term we call a radian. A radian. It is very important we also state that the angle we call angular displacement is given in radians. In radians. Then after that, now we can define what a radian is. We can define what a radian is by first of all considering we consider S being equal to r. So if s equals to r, this shall imply that the angular displacement will be 1. And this is 1 radian because the angle is measured in radians. Therefore, 1 radian can be defined as the angle in radians, the angle subtended at the center by an arc length which is equal to the radius of the circle. So if we have an arc which is equal to the radius of the same circle, then at that moment angular displacement becomes 1. And when angular displacement is 1, then that gives us 1 radian because it is the angles measured in radians. And now that derives the definition of a radian, which is the angle subtended at the center of a circle by an arc length which is equal to the radius of the circle. So now we can look at angular velocity. Angular velocity, it's abbreviated a Greek word called omega, which just looks like a twisted W. So angular velocity is the change in angular displacement, with time. The change in angular displacement with time, such that omega is given by the change in angular displacement, which is theta, with time. So change in angular displacement with time, or angular displacement over time, gives us angular velocity. With this we can remember the first equation. It's good we recall the first equation, which says that angular displacement is s out of r. This means if we divide this equation, we divide the equation by time t, we can divide this equation by time t such that theta out of t equals to s out of r and t. And if we take small changes on either sides, then we shall arrive at change in angular displacement out of change in time, which will give us change in the distance or the arc length out of r and change in time. We know very well that this one gives us the definition of omega. This one is omega. Therefore, omega, this is an implication. This implies that omega equals to, when we take change in s out of change in t, we get velocity v according to linear motion out of r, because there is a radius here. Then this can imply that v equals to, when we multiply through by this radius, v equals to omega r. So velocity equals to omega r. In this derivation, we are just realizing that a body in a circular path is possessing both angular velocity and linear velocity. In other words, we can just mention the statement that a body in circular motion, has both linear and angular velocity. So a body in a circular path, or a body in circular motion, possesses both angular velocity and linear velocity in the relationship v equals to omega times r. So that is the relationship between angular motion or angular velocity and linear velocity. It is important we mention that if the body which is tracing a circular path is released from any instance, it was having angular velocity, but when it released, it follows a straight path using a certain linear velocity. Therefore, that is why we say that a body in circular motion has both linear and angular velocities. Thank you for following. Kindly subscribe to Shifting Grades. For any clarifications, follow me through 0704 153 366. Thank you.